somewhere deep in the bowels of the Microsoft 365 portals, of which there are many, somewhere in there, there is a setting that says bounce emails if they're not originating from a client in the United States. I'm certain that is there. All of my furious Googling has resulted in nothing. And trying to actually pry open the various layers that Microsoft has created is an exercise in futility.
I mean, you saying you can't do it with PowerShell? I was told you can do everything with PowerShell.
I hate you so much. Hello, alleged human, and welcome to the Chaos Lover podcast. My name is Ned, and I'm definitely not a robot. I'm an illegal immigrant coming in from Canada to steal all your American dollars. Is that what we steal? I don't know. With me is Chris, who is also here. Chris, I'm still in the same time zone, but somehow I'm jet lagged.
That'll happen. I assume you drove.
Yes, indeed. That was one of the bonuses, was that we didn't have to go to an airport and deal with the TSA and children.
Right. Wait, which one's worse?
Yes.
Fair.
Am I calling the TSA a bunch of children? That's for the listener to decide. Oh, don't revoke my TSA pre-check, please. Yeah, we crossed the border with nary an incident into Canada because the Canadians make it easy. And then it took an hour and a half to cross the border back.
Nice.
Because America.
USA.
There's more to it than that, but that's the bit that I'm going with for now.
That's fair. I mean, I'm sure it had nothing to do with the 5 tons of contraband maple syrup you were trying to sneak over.
4 tons, and we had it in a compartment that they'll never find. That's what the minivan is for, the false bottom and all.
It's like the TARDIS in a number of ways.
Indeed. The border guard had a lengthy conversation with us about college sports. It went on for like 3 minutes, and I was like, there's a line going back like a mile and a half. And you're like, so how's Villanova doing? And we're like, good? Can we go yet? I was like, I think I might know why this is taking so long.
Might have an idea.
Little chatty Cathy going there. But he let us through, and we got back into the United States with my cover intact. So that's good.
The perfect not crime. Yeah.
Right. So I took a break from my bath in maple syrup to come record this episode. So I guess we should do that. What are we talking about, Chris?
We're going to talk about and not talk about.
I know what's coming.
2025 has been declared by the United Nations as the year of quantum science and technology.
Does the United Nations often declare years as having a scientific theme?
Apparently they do it every year, and by that I mean they've at least done it twice. I'll get back to that point later.
Have you pretended to read Infinite Jest like the rest of us?
No, I actually read it, unfortunately, and it's affected me.
Deeply. Yeah, I was going to make the year of the Glad trash bag joke.
Ah, yes.
That's also the book that taught me what disseminate means. So that's exciting.
And eschatology.
Indeed. So quantum.
So yeah, it's the United Nations, man. It's cool that they did this, right?
Yep.
Why not? They decided on it because it is officially unofficial that 1925 was the year quantum mechanics became real, formalized, accepted, mathematical thing.
Okay.
Right. Now it's hazy, but that's the year. And we'll figure out why, maybe. Because there's a lot to talk about, and we should talk about it. Because without quantum mechanics, obviously, you wouldn't have quantum computers.
I mean, who's going to fix the quantum computers when they break down?
Quantum monkeys with quantum wrenches.
Would you call them quantum mechanics?
Oh my God. Go back to sleep. One major reason that people don't understand quantum computing is that they don't understand quantum mechanics. Nailed it. First try. Every time.
50% of the time, you get it 100% of the time.
So here's the thing. Quantum mechanics flies in the face of everything that seems logical about the world that we live in. So There's also a lot of vocabulary. Here's an example quote describing the critical difference in weirdness about quantum computers. Quote, "The principle of superposition, fundamental to quantum mechanics, is what gives quantum computers their power. In quantum computing, performing an operation on a qubit in superposition is equivalent to performing the operation on all possible values simultaneously."
All right.
Got all that?
Yep.
Yeah, me too, completely.
Okay. End of episode. We
And
did
that's
it.
all the time we had. So for everybody else that might need a little bit of help understanding what in the hell is going on, how it's possible, and why, which is that's the hardest one to answer, I thought it would be fun to take a little gamble through space and time, but not space-time. We do not have time for that. And just try to shed a little light on how the hell we got wherever it is we are right now.
Okay.
And so I wrote that expecting to get to today, and I did not get to today. So we're going to get a lot of the way there.
Fair.
So we need to do a little history to understand where we came from, how we got here. And I swear to God, there's not going to be any math. Well, okay, there's definitely math involved. But
Right.
since I am not a mathematologist, I'm just going to tell you what the math proves without delving into any formulas.
And I appreciate that because I suspect all of those formulas have 0 actual numbers in them.
There's a lot of Greek symbols.
You know, just as a quick aside, when I started taking trigonometry and then later calculus, no one ever sat me down and explained what the different Greek letters were and how to properly write them.
Oh, that makes it more difficult.
And they were just like, here's a delta. You know what delta is. And lambda, here's a lambda, and there's a sigma. And you just had to kind of either pick this up on your own or hope somebody else filled in the gaps for you. Maybe just one day. Or maybe I was absent that day. Who knows? But like, here's the 5 Greek symbols we're going to use this year, how to pronounce them, how to write them.
How to do it on a keyboard. We're way too old for that. What am I kidding? Ugh.
Keyboards.
Anyway, let's go back to the beginning where we began. And we can only say this with a little bit of an asterisk because I am certain, and historians are certain, that humans have been wondering about this question since we learned how to wonder.
Okay.
But we can only work with what was written down. One of the first major efforts to understand the world around us that was not obvious, in air quotes, was trying to understand light. And it goes back a long time. Because you don't have to be a scientist to know that light in and of itself is weird.
Yeah.
Some light is harmless, like, the 60-watt bulb in the closet. Some light is so intense that it can burn your skin. Light doesn't even have to be generated by electricity or fire. Here's an example. Go get a framing nail, one of the big ones.
Okay.
And a solid piece of wood, not a word from you. And just blast that nail a few times. As long as you hit it square and you hit it hard enough, eventually it'll start to glow, aka emit light. Now, I know you've never actually worked with your hands, but I promise this happens.
That's fair. I've been called panda hands in the past.
I am not delving into that. No follow-up questions.
Fair.
So, if you look at sources, even ancient philosophers, scientists, because there really was no separation between those two for a long time, recognized that there was a correlation between light and heat, and it had something to do with eyes.
Yeah.
Because you need those to see the light, right? But light can affect other things. Like, what the hell's going on?
Yeah. You could see if something was underwater, you could see that it kind of refracted things in a weird way.
Right.
Or if you were underwater yourself and looking up, you could see that I sort of see the reflection of myself, but I also see what's like light does a lot of weird things in different mediums. And why is it doing any of that?
Right. So, in order to save time and make this less than a 12 episode arc, I'm going to skip roughly 2,000 years of exactly this kind of philosophizing. And I'm not exaggerating. In terms of what is written down, this shit goes all the way back to Pythagoras, who, yes, he was a real person, and he was fucking weird.
He was real weird. The word cult is thrown around, and it's not wrong.
A number of times. It is not just A squared, you know the rest.
Yeah.
Anyway, this is going to come up with a lot of these scientists, where there's going to be an aside where I'm just like, and he was fucking weird.
Yeah. The next person you bring up, I suspect.
I will leave the bulk of that research out, though, as, a fun little exercise for the reader.
Mm-hmm.
So let's fast forward to the 1700s and a guy you might have heard of called Isaac Newton. And he was fucking weird.
His cookies are weird too.
So, Newton posited the theory, or supported the theory, I should say, that light was a particle. It traveled in a straight line unless it interacted with something, in which case it would bounce off, reflect, etc. Reflect?
Yes.
Refract.
We're all reflecting.
Every day I'm reflecting.
Tough acting, reflecting.
This is going good.
It is.
He did this in direct contrast to another scientist named Christian Huygens. Apologize, by the way, in advance for all pronunciations. Huygens in 1680s had the idea that light was a series of waves that were emitted in all directions. Now, you can see that there was philosophical reasoning behind both positions, though, right? Wave theory, as we understand it, you write a wave, it's got peaks and valleys, and it's regular, and it goes across for as long as it needs to go across. This was understood because even in the 1680s, we had water.
Yeah.
We had ponds. You could throw a rock in a pond and watch the waves come out from the impact point, perfectly concentric circles, evenly distributed in all directions. So understanding what waves were, pretty natural. Newton, by contrast, showed, using his own mathematics, that he could explain reflection and refraction without waves being involved. He could do it as particle science. And he published it in, I think the book's called Optics with a K at the end, because they spelled things way more fun back then.
Indeed, they did.
And his argument held sway for a century, primarily because A, he was the hottest shit in science and the most influential. And let's just say he didn't treat his competitors kindly. But B, there wasn't what we could consider evidence that proved the case for either side. This was just theoretical at this point. And experimental science and theoretical science often lag one behind the other. They don't follow evenly. And you see that through all of scientific history, not just physics or mathematics.
Right. It's the fundamentals of the scientific method. You come up with a hypothesis and then you test it. And until you can test it, it's really hard to make it a theory.
And as we will see later on, sometimes, especially as we get more and more modern, testing this stuff gets real hard.
Yeah.
So we were in the 1700s. Light might be a wave, light might be a particle. Let's move forward to 1801. And an interesting scientist, who I don't think was a fucking lunatic, named Thomas Young, had an idea for a way that this could actually be tested. First, though, let's think about this from his perspective as a thought experiment. Let's say you have a flat piece of wood, 2 feet square, just something hand-holdable. And in the middle of the block, you cut 2 perfectly parallel slits, each one about half an inch wide, maybe half an inch apart. Something very consistent. Now hold that about a foot off the ground and pour a bucket of sand so that the flow of the sand hits basically exactly in between the slits, both slits at the same time, right? What's going to happen to the sand?
I mean, in my mind's eye, I would see the sand would fall pretty evenly through both slits.
Right. You should basically end up with 2 piles of sand, roughly the same size and shape, directly below the slits, right? That's what your intuition tells you, and also what should happen with light if crazy old man Newton is to be believed.
Right. If they're particles, like sand is made of particles, they should go through the 2 slits evenly. You should have the same concentration of light under both slits.
And since light particles are so infinitesimally small, it should also be very sharp edges.
Okay.
Not like little haze or anything like that, because light is way smaller than grains of sand. Well, Young decided to test this, setting the stage for what has become one of the most famous experiments ever. Using a dark room and basically an index card, Young proved that far from behaving like a particle, light clearly showed interference patterns as though it were a wave. This so easy a caveman can do it experiment was then double proven with a more scientific and rigorous double slit experiment.
Okay.
Which, amazingly, is also super easy. And you can do it at home. I know this because I did it at home.
Wow. I am impressed by the level of rigor for this episode.
I know. I'm waiting for my PhD to arrive in the mail. Now, Similar to the example that we talked about with sand above, in order to do the double slit experiment, you get a source of light. In modern times, it's usually a laser pointer because that's the easiest way to do it.
Mhm.
And you get two slits that are parallel together on an opaque surface. Now, if you want to do this at home, the easy way to do it, you can just buy a scientifically designed slide that is built to do this experiment in like high schools.
Mhm.
If you want to do it the Etsy way, you can just cut two slits in aluminum foil with an X-Acto knife and then paste them onto a card with a hole in the middle to hold the aluminum foil so it doesn't crinkle. If you do that, make sure you're using the non-reflective side because reasons. And yes, aluminum foil has a non-reflective or at least a less reflective side.
Okay.
It's true. I'll give you 5 minutes to run to the kitchen. Also, pour one out for all of the index cards and aluminum foil that were lost in this scientific endeavor
Fair.
because it was substantial. You have your slits, you have your card. All you do is aim the laser pointer right at the slits.
Okay.
Now, once again, what do you expect will happen? You think it's the sand thing, or do you think it's something else?
I kind of know it's something else. Let's just jump to that.
I should have interviewed your dog for this one. You're right, of course. You do not get two hard-edged bars of light illuminated on the wall like the sand. You get is a long line of bright, then dark, then bright, then dark, then bright, then dark, etc., moving outwards until it stops being visible on the periphery, called an interference pattern, which is exactly what would happen if you were using waves. The light waves hit each slit, separate into two separate expanding semicircles of waves that are interfering with each other in a regular geometric pattern. And the way that it works is very simple. You have a wave that has a, what's it called up top?
A crest?
A crest. And another wave that has again?
The trough?
No, dum-dum, a crest. Two crests hit together and it makes a bright point. Two troughs hit together and it makes a dark point. A crest and a trough hit each other and you get nothing. So what do you end up with? Bright, then dark, then bright, then dark, then bright, then dark. All the way across. And honestly, the light goes way farther than we can actually see. If you look this up on YouTube, there are some people that did this in serious laboratory areas, and it is consistent for really long distances, and it does not matter how bright your light point is. It only matters, like one of the main reasons you use a laser pointer is it's incredibly bright and it's incredibly concentrated. So it's easy to see with the naked eye.
Right.
If you didn't have the naked eye, if you had, say, photosensitive paper, you could see this no matter what.
Wow. Okay.
Make sense?
I mean, what you're explaining makes sense. That's acting as a wave, but it still seems weird.
It is weird, and it only gets weirder. Now, interestingly, and I brought up the lake earlier for a reason, which is you can simulate this experiment on a calm body of water. If you create a repeating wave pattern by, say, I don't know, getting a paddle and smacking the water rhythmically, and you put two separate slits out X amount in front of you, you can actually watch the wave, the single wave hit the two slits, become a double wave, and cause those same interference patterns as they go out into the lake.
That is cool.
That is pretty cool. And sometimes messy, and it upsets the frogs. So don't do it for too long.
I won't.
Now, in order to create those interference patterns, you need more than one wave, right? I mean, obviously, we just talked about that. One wave hits two slits, causes two waves, they interfere.
Right.
We're going to fast forward a little bit. And we get to a point with experimental equipment where you can literally send only one photon at a time at the slits. What do you think you're going to get?
Well, I would think if it's just one photon, it would have to go through one slit or the other. It can't go through both.
Oh, you sweet summer child. We tested this, and actually, it took a long-ass time. It took until like the 80s to do this experimentally. But
Well, isolating a single photon is not easy. They're super tiny.
yeah, they weren't doing that in the 1800s for some reason.
Ugh, slackers.
But if you put a photosensitive paper or plate behind the two slits and fire one photon at a time and wait, they will show up as an interference pattern, exactly like if it was a full wave.
That makes no sense.
Now, here's my question to you. How in the hell is this possible?
Well, God, I hope you're going to tell me because I got nothing.
What ends up happening, and the easiest way to explain it, is the single photon going through this apparatus is interfering with itself. And to quote my main source for this episode, which is the amazing book Through Two Doors at Once, quote, "This is rather curious." How is that
Holy
for an
shit.
understatement?
Yeah, that's a bit of an understatement to say the least. Okay, so a single object is interfering with itself to create an interference pattern that, in my mind, should not exist.
Correct. And this is absolutely provable, and there's no question that it happens. It has been tested hundreds of times in hundreds of apparatus.
Are we sure that aliens aren't just fucking with us?
Are aliens even real if no one's there to observe them?
Think about it. Yes, they are. I'm not a solipsist.
I'm not going to go too much further down this particular rabbit hole today. I might do it later. The reason that I bring this stuff up is not to do a math lesson. It's really more of a open your mind to the insanity and wonderment that is the quantum realm. And it is far, far weirder than you could possibly imagine. And something interesting comes of this that starts to really inform how we have to handle anything at this size. And by that, I mean in the quantum realm. And that is, you can never know for sure where in that interference pattern the photon will land. You can not even know for sure which slit it goes through. You can only calculate, and I promised that there would be no math, you can only calculate the probability of it landing somewhere within the range established by the conditions of the slits and the photosensitive receiver.
Hmm.
And that forms the basis of all quantum mathematics. It is, remember, a qubit plays this same game. A qubit can be any value between 0 and 1, and it is a probability that we are going after. And that's also the reason that quantum computing calculations are run hundreds and hundreds of times, which is an interesting thing that I'm not going to get too much more into today, but I might do later, as soon as I get to that chapter.
Okay.
So I'm asking the audience to just embrace the weirdness. And I'm going to ask another question. If you set up a mechanism wherein you know for certain which slit the photon goes through, what do you think happens?
You collapse the wave and the interference pattern goes away. And I'm saying that because I know that's the answer. Not because it's obvious.
That is correct. Now, like I said, these single photon experiments didn't happen until much, much later, but the behavior I talked about was known and explained mathematically. But I did promise that there would be no math.
Mm-hmm.
So I won't do a math. In short, between 1901 and 1928 was some of the most interesting and dramatic changes in the way that math was talked about by some of the smartest people who have ever lived on Earth. There was this one guy, an obscure little dude called Einstein.
Doesn't sound familiar.
He proved that light was quantized into a discrete series of packets, or quanta, hence the time that we started using these terms colloquially, called photons. Now, the idea of quantize is an amount.
Mm-hmm.
The idea of quanta is the smallest possible amount. AKA, for these equations, for these experiments, etc., this is as small as it gets. And that's an interesting concept too, which again, I don't have time to get into, because it's not like you can have a third of a photon, right? That stands to reason. But what does that mean? You can't have a third of an electron. You can't have a third of an electron having a certain amount of energy. How do they jump between one level or another? Like I said, there's a lot that I'm not talking about.
I know it.
Yet I'm talking about it. But Einstein did that in 1905, and he won a Nobel Prize eventually, because Nobel Prizes are weird. You can win them like a decade later.
Yeah.
I don't get it, but whatever. I always thought it was like the Oscars. It's not like the Oscars.
It's actually kind of like the Oscars, because people tend to win Oscars not for the movie that they starred in, but as a sorry, we didn't give you the Oscar for the movie you were in 10 years ago.
Oh, that's true. Yeah, that's a good way to think about it.
It explains Scent of a Woman perfectly.
Wow. Yeah, so long story short, fun fact for the episode, Einstein didn't actually win the Nobel Prize for E equals mc squared or relativity. He won it for this work on the photoelectric effect. So there, I just answered an impossible round Quizzo question for you. You're welcome.
Oh, thanks, buddy.
So at this point, things do get obtuse and very, very mathy. It's really annoying for me to do this, but I'm just going to say a lot of stuff happened. There was a huge argument understanding what an atom really looked like. Spoiler alert, the image that you have in your head of electrons is wrong.
Yes, completely wrong.
Once again, it is not like a planet in the middle with moons orbiting it. The planet in the middle part, sure, even though not really. But around them is a cloud, and in that cloud is electrons. And where the electrons are in there, in mathematical terms, the only way we can describe it is who the fuck knows?
They're somewhere around there.
Right.
And sometimes they're not.
So that all got weird. And then in 1924, another scientist named Louis de Broglie made a shocking proposal. What if it wasn't just light that behaved as both a wave and a particle? What if matter did too?
Dun, dun, dun.
Long story short, too late. This was proven to be correct. In 1925, we got there.
Yay.
Matrix mechanics was developed by a guy called Heisenberg, not the one that sells drugs, to formalize the mathematical descriptions of probabilistic calculations. Because by this time, everybody understood at least this much. There is no definitive answer to the question of where is this particle and how fast is it going? Now, this is the uncertainty principle, right? I did not exactly say it the way that it is written because we, as non-scientists, tend to oversimplify it. But really, all it does is reinforce the concept of certainty not existing in the quantum realm.
Mm-hmm.
Observation changes things. And if we're not observing things, things get even more complicated, which I'll get to in the conclusion.
Okay.
So matrix mechanics happened. There was a lot of argumentation. There was the Copenhagen thing, where very famously a couple of scientists spent about 4 months hanging out in their attics and arguing with each other about this, which I'm sure was fun for the housekeeper.
Oh, sounds like a disaster.
What else happened? Schrodinger, you might have heard of him.
He's the guy with the cat.
He did the cat thing. He did a lot of other stuff too. The cat thing came later. Early on, he invented what's called wave mechanics, another form of math that calling it a replacement from matrix mechanics doesn't make sense. In reality, they both are still used and they're used to solve for different problems. And the matrix mechanics, just to be as precise as I can, matrix mechanics was an algebraic approach employing the technique of manipulating matrices. Wave mechanics employed differential equations and had a basic partial differential wave equation at its heart. And I could explain that, but we're running out of time.
Indeed. And you can't explain it.
Shit.
I like that you tried, though.
All of that happened, among a few other things. I want to stop here, though, because it's a good point to stop at. Because it does... Honestly, we could probably do an entire episode just on 1925 through 1928. But we also don't want to go too deep into the physics per se, because this is not a physics podcast.
Not yet.
Dude, you don't know how close it came to being a historical weirdos podcast.
Oh, Chris, I have something to tell you that may have already happened.
But anyway, there we have it. The short version of how we went from Newton to quantum mechanics. Quantum mechanics, as again, proven to work over the past 100 years, many, many times, shows clearly that all matter is composed of small, individual stuff that we call energy. It becomes mass, it adds up to atoms, which become molecules, which become Xboxes. The quanta simply don't behave like the Xboxes do. Quanta do things like superposition and entanglement, which make quantum computing possible. Xbox just lets you play Fallout for 7 hours when you should be writing term papers. So I've heard.
Right.
The amount of weirdness that I read and ultimately left out for clarity and a minimum of tangents was absolutely astounding. Like this. Did you know there is a huge argument about the observer effect? To wit, the theory that if we don't observe something, or something isn't observed, I should say, because it really is not humanistic in this way. But if something isn't observed, it doesn't exist. Ergo, for certain arguments in quantum physics, the question, if a tree falls in a forest and no one's there to hear it, does it make a sound, could theoretically have a different answer.
Mm.
Nobody could hear it, then nobody could see it. So, what tree?
I don't like that, and it makes me uncomfortable.
Oh boy, will I send you a paper that will ruin your day. Einstein famously rejected this all through his life and spent most of the rest of his life trying to disprove it. One of his biographers, A. Pace, recalled, quote, "During one walk, Einstein suddenly stopped, turned to me, and asked whether I really believed the moon exists only when I looked at it." Which, fair? I mean, one thing we know for sure is the moon is absolutely not a dragon egg.
Hmm. I will say that you mentioned video games in passing earlier, and the virtual worlds that we build with video games and the way that they're rendered lets us put this in a different perspective of the fact that as an observer inside the video game, are things happening outside of what I can observe inside the game? The answer is yes. So that's why I think that the answer broadly, are things happening in the universe when I'm not there? The answer is also yes.
Where's your physics PhD from again?
Shut up.
I've got a PhD from Ultima Online. That'll tell you. So, of course, like I said, this is an argument. Other scientists have refuted Einstein on it with even crazier, but apparently mathematically feasible statements like, quote, "Observations not only disturb what has to be measured, they produce it. We compel the electron to assume a definite position. We ourselves produce the results of our measurements," unquote. As the kids say, quantum physics be cray.
Yeah.
And they're right, man. It do be cray.
Cray cray, even.
And I want to end, I'm actually going to throw in one bonus craziness. Let's pretend, I'm going to do a thought experiment, and it's not going to take too long. Let's pretend we have an electron that we have control of and can fire through detectors at will. Okay? The electron has two properties to it, and only two properties. It is either a black electron or a white electron, and it is either a hard electron or a soft electron. That's it. Two categories, either or. And we have built detectors for the color and the hardness. So the electron goes into the color detector and it comes out of one of two chutes, either black or white. So we know for certain it goes through the white one, it's a white electron. If we test it again, it's a white electron. If we send that electron through the color detector and then through the hardness detector, what should we get?
We should get both properties.
Right. You should know for sure that, for example, it's a black hard electron.
Okay.
Right? Because these were 50-50 questions. There was no ambiguity. Now, here's my question to you. We take that electron, we send it through the color, we send it through the hardness, and then we send it through color again. We go through, and it's a black electron. We go through the middle, and it's a hard electron. So it's black, hard, going into the color detector again. What are the percentages of it coming out as a black electron again?
It should be 100% that it's going to be black, but the probability is still 50-50.
That is absolutely correct. And that is bazooka. Now, the only thing that I changed about this to make it more understandable is the types of things that we can measure with electrons. So we could also measure spin, momentum, blah, blah, blah. But this is a much simpler crayon example. And again, it has been proven experimentally hundreds of times. There are certain things about the quantum world that are just so insane that even people that understand it kind of don't understand it. And I read something about trying to understand it and the pointless nature of that. And the quote read something like, trying to understand the nature of these probabilistic experiments is like trying to ask the weight in grams of Catholicism. It's just not a question that needs to be asked or can be answered.
It's 26, but, because it's double 13. Don't worry about it. It all makes sense theologically.
Oh, and one last note. Remember how I said that 2025 was going to be the year of quantum from the United Nations?
Yeah.
And that's pretty cool of them to do.
Yeah.
And that there were other things. You want to know what 2024 is the year of for the United Nations? I'm going to let you guess.
Is it blockchain?
No, thank God.
Okay.
I would have had to start a United Nations war.
Ooh. Is it the year of peace?
Oh, angel.
Sweet angel baby. All right, I give up. What is it?
2024 is the year of camels.
Oh,
We're cameloids. We're camellaries. And while I was writing this joke, I realized that actually camels are probably pretty cool too. So whatever, man. Let's tune in next week for our deep dive into camels. But not quantum camels. Or are they?
Ooh. And if you really want us to do an episode on camels and how they're related to technology, I would 100% fucking do that. Just go to chaoslever.com and leave us a voicemail or a message or a comment or whatever and say, I want the camels episode, and we will make it happen somehow. Oh, hey, thanks for listening or something. I guess you found it worthwhile enough if you made it all the way to the end. So congratulations to you, friend. You accomplished something today. Now you can go sit on a couch, grab an index card and some tinfoil, make your own double slit experiment. You have earned it. You can find more about the show by visiting our LinkedIn page. Just search Chaos Lever or go to the website, chaoslever.com. Yes, I redirected the Apex domain, so it all just works now.
Wow.
You'll find the show notes, blog posts, and general tomfoolery. We'll be back next week to see what fresh hell is upon us. Ta-ta for now. The redirect was actually really easy.
And why did it take you 6 weeks?
Shut up.